Yeah.
All right. All right, so I'm Steve Hodegger. I want to talk today about quantum computing. I'm going to try to avoid being nervous. I'm going to try to just keep this informal, nerd out on the topic, and just we'll see what happens.
So I guess you're on camera.
Okay.
Nope, you're fine. Just stand right
Okay.
Just as you're
So-
talking about relaxing, move to the left, right, 2 feet.
All right. So first of all, I'll say that as far as quantum computing goes, obviously it's not something that we're going to use tomorrow. But as technology advances, it's on the horizon. It's coming sooner or later. Advances are being made every day. Why do we want to study quantum computing? Well, there are a lot of applications for quantum computing, including cryptography, authentication, data compression, some database functionality. One of the algorithms that we'll look at today could potentially be useful for database lookups. And others, new algorithms are being discovered, and with the tools that we'll look at today, I mean, if you guys want to play around with it and try to figure stuff out on your own, you might come up with something new as well. So a quick overview of what I'm going to talk about. I'm going to start by going over some of the math that will hopefully be helpful in understanding what's going on in quantum computer. Just some basic quantum physics that should be helpful. Then we'll go over what makes up a quantum computer in the abstract. And from there, look at a few algorithms, and then actually building out those algorithms in the form of a quantum circuit using IBM's quantum experience. This is something that I think just came out earlier this year. They've built where you can build out a quantum circuit or import a quantum assembly program and actually run it in the cloud on their actual physical quantum device. If we have time after that, we'll go over a quick survey of some of the software that we might be using to develop quantum programs in the future, and then hardware. And then if we have any time after that, we'll do some questions. All right, so there are two kind of disciplines of math that are going to be important for us. First is complex numbers. Start with the imaginary number. Probably seen this. I is just the square root of -1. So there's no real number that solves this equation. So we have a new set of numbers called the imaginary numbers that fits that. Now we've also got complex numbers, which is a combination of reals and imaginaries. Complex conjugate is just taking the sign on the imaginary portion of a complex number and reversing it. And then we've got the modulus. So you'll see here the modulus of a real number is just a special case of the modulus for complex number. It is the absolute value. One way it could be defined is as the positive square root of a squared. So we're just taking away the sign. So for the complex case then, the modulus would just be the square root of a squared plus b squared, the real part plus the squared plus the imaginary part squared. The next formula you might know, if you remember any geometry, you might realize that looks a lot like a distance formula. C squared equals a squared plus b squared. C, of course, here is a complex number, but this is going to be really useful in visualizing what's going on with our qubits. And then lastly, another way to write that is helpful is that the modulus of a complex number is equal to the complex number times its complex conjugate. Going on with this, we can see the kind of Cartesian representation of a complex number here. we can actually take the imaginary component and the real component, plot them on a two-dimensional coordinate system. We can also represent this not only in terms of the Cartesian x and y coordinates, but also as a polar representation. So here, p is the modulus, the length of the vector that is created from the origin to the point, and then cosine theta plus I sine theta. So we can also envision this vector, this complex number, as having a rotation around the origin of angle theta. One useful formula, it's just kind of handy sometimes, is Euler's formula, which you'll see looks a lot like the polar representation for the complex number, and is in fact equivalent when the modulus is 1. And this is just saying this number is equal to a rotation of the angle theta. Matrix multiplication, if you were in the same talk I was in just now, you got some of this. This is just when we multiply two matrices together. This would be, in other words, the inner product. There's different kinds of multiplication. This is the inner product, but we can just call it matrix multiplication. So to get that upper left-hand corner, what we're doing is we're multiplying the row of the first matrix by the first column of the second matrix, and then we're adding the results. So 1 times 2, and 2 times 1 is 2 and 2. 2 plus 2 is 4. It's not that hard. We also have the tensor product as another kind of matrix multiplication. This will also come in handy here. We're basically just taking one element of the first matrix, multiplying it by every element of the second matrix, and that becomes a submatrix of the result. All right, so quantum physics. So I want to go, I don't have a whiteboard. I want to go over real quick because one experiment that might be familiar for a lot of you is the double slit experiment. Okay, so this is where you have a wave. You can first imagine a water wave hits a wall with two pinpoints in it. The waves then propagate from those two pinpoints, and when those waves are in sync with each other, same phase, they enhance each other's amplitude. The wave gets bigger. When they are opposite each other, they cancel each other out. So what you end up with is, on the opposite wall, you see a pattern of large waves and then just no motion. So the same thing happens if you do the experiment with light. So light acts like a wave, and when you shine a light with two slits, what you see is an interference pattern where there are bright spots and there are dim spots. So the interesting thing about this is, if you do the same experiment one photon at a time, you get the same interference pattern. So the probability distribution of doing multiple photons, one photon at a time, is the same as that amplitude distribution with bright spots and dim spots. The reason for that is that that single photon is actually interfering with it itself. So this is very key here. It is literally in multiple states at once. Another way to think of it is as a wave, and it is interfering with itself, but when we measure it on the opposite wall, the state of that wave collapses to a single value that we measure. So whenever we observe something, we see a single value. But before that, the state can be in many states all at once. And there is no way to know what that superposition is other than to do the measurements or to do the math based on what operations have been done on that. So I wanted to give a real quick kind of real life example of how this works. So I've got here a couple of polarizing films. These are the same thing that are in your 3D movie glasses when you go to the movie. So in your glasses, you've got a vertically polarized filter on one lens and horizontal on the other. So these are basically constructed from long chain polymers that represent kind of a grating that restricts only certain polarized light to go through. So this is how you see two different images in two different eyes. What that means is that vertically polarized light can't go through a horizontal filter and vice versa. So I don't know which one this is. It's horizontal or vertical. Doesn't matter. The other one is the other. All right. So if I take my laser and I shine it through, you can still see it kind of there. If I put the other one behind it, nothing. All right. I'm first filtering to vertical and then to horizontal. So I'm filtering everything out. All right. So I do the vertical. I get vertical polarized light. I do the horizontal. I get nothing. Now what happens if we change this up a little bit? I can do the vertical polarized filter. I get vertically polarized light. Now what happens if I do a diagonally polarized filter? Well, with respect to the diagonal filter, there is no defined state, okay? Or rather, it is in a superposition of states. It is both, if it is what we have is vertically polarized light, but measured in a diagonal basis, it is polarized both vertically one way, and both diagonally one way, and diagonally the other way. So what we do when we do the diagonal polarization filter is anytime we're doing a filter, we're actually doing a measurement. We're observing the state of the polarization because only certain polarizations get through. So when we do this, we now measure that some of the light is polarized diagonally in this direction rather than the other diagonal. So then what happens if we do a horizontal after that? So what happens if I take this, got no light coming through, and I stick, you might be able to see it, the diagonal, I've now got light coming through. Only a little bit, because it's been, the amount that's coming through has been split in half a few times. But, so classically you would think, well, I've got two barriers here, and I'm putting another one in. How, by filtering more, am I allowing, to let more through? So what's happening is the diagonal filter is actually doing a measurement, and that changed the basis so that now the light is polarized diagonally, which means that with regard to the vertical horizontal basis, it is in a superposition. And when you measure it again, now it could be either vertical or horizontal. So one thing that I want to go over with regard to bits, how we look at qubits. So obviously, when we're doing computing, we're working ultimately with bits of information, zeros and ones. So on the left-hand side, we've got classical bits. You might be tempted to think of a qubit as a probability distribution. There is a given probability that when I observe it, it will be a 0 or a 1. In fact, there's more to it than that. There is not just a single dimension along which a qubit exists. It actually can be viewed as on a sphere, which we call a block sphere. And this is where some of the polar representations of the numbers come in handy, because we can view the state of a qubit as being somewhere in a rotation around this sphere. So this is my block sphere. I've got a z-axis, a y-axis, and an x-axis. You can see I've got, so what we have here is, if the state of the qubit is up here, then I'm going to measure a 0. All right. If it's down here, I'm going to measure a 1. If it's somewhere on the equator, then I've got a 50-50 chance of measuring either a 0 or a 1. But the other thing that comes into play here is the rotation then around the z-axis, and that's known as the phase. And where that really comes into play is does the state of the qubit, what does it have to do with the states of other qubits? So if it weren't for the phase, we would just have a bunch of different bits that might go to 1, might go to 0. But the phase it also allows for a hidden, well, the operative word is entanglement between bits, so that the state of one, when measured, depends upon the state of another. So let's get on to architecture. Okay, so our qubits, if you look at a single qubit, we can envision its state as a vector. In addition to the block sphere, we can look at it this way. So we have complex numbers in 2 locations in a vertical vector. With the first represents 0, the second value represents 1, and actually the modulus of this value is the probability that you will measure it. So here we've got 1 over square root of 2i. If we take the modulus of this, the I is going to drop out. We're going to have 1 over 2 for both values. So 50-50 chance of measuring a 0 or a 1. We also want to talk about state transitions. So every operation that we do on a qubit can be represented by a matrix. It has a few restrictions. So the term to remember here is the matrix must be unitary. We'll talk a little bit about that more later. But essentially, an operation on a qubit will be simply equivalent to multiplying that state by a transformation matrix and getting a new state. So here, if we were to have this kind of transition, we'd be going from a qubit which is equal to 0, doing some transformation on it, and now we've got one. This is actually kind of meaningless because there wouldn't be any rotation if it's all 1. But anyway, this guy on the right is going to collapse to a 1. So here's where that was the inner product, the matrix multiplication part. Here's where the tensor product comes in. So if you have multiple qubits that are not entangled, they're independent, but you want to act on them with a single transformation, then if we want to represent that in terms of matrix, we take the tensor product. So this gives us the amplitudes for all 4 potential states that we get by having 2 qubits. So you can see here, if this represents the first bit and this represents the second bit, then the amplitude of 2 zeros is going to be specifically this value because this guy's always a 0. And the chances of having a 0, 1 is 0 because this guy will never be 1. And likewise for these 2. All right, so now let's talk about how this works for classical logic gates so that you can kind of get a feel for how this is working. So the first is the identity. This does nothing. You would never actually have this as a logic gate in a computer because it's just equivalent to a bare wire that transmits a bit. You've got the NOT gate, which flips it. So you start with a 0, you get a 1, and vice versa. Here we've got the columns represent input and the rows represent output. So in a classical AND gate, we're going to get a 1, we're going to get a 0 out unless we have 2 1s, and then we're going to get a 1. OR gate, we're going to get a 0 if we have 2 zeros, otherwise we'll get a 1. And exclusive OR, we will get a 0 if they're the same, and 1 if the 2 bits are different. Quantum logic gates. So let's look at the block sphere again, because this will be helpful in seeing what these transformations are doing on our individual qubit. So we've got the x. Now, that's exactly the same as the classical knot. It's taking a 0 and making it a 1. So it's called x because it's a rotation around the x-axis. So if we were to start with a 0 and rotate around this axis, 180 degrees, we end up down here at a 1. So it's a knot. It flips zeros and ones. Of course, if you start somewhere else, maybe on the equator over here, you're going to rotate all the way around to this side, changing your phase, but not the probability of collapsing to one state or another. A y is just a rotation around the y-axis. Z is a rotation around the z-axis. S is actually a 90-degree rotation around the z-axis. So I could go from here to here, or here to here. And then T is actually the square root of S. So you'll notice here we've got Euler's representation. So this is just helpful here because we know that this represents a rotation of pi over 4 radians. So if you remember radians versus degrees, that's 45 degrees. So here to here. So that's equivalent to the square root of S because if we do it once and then again, we get a 90-degree rotation. Hadamard is actually 2 rotations, and that's going to take you somewhere on the horizon. So you can. Hadamard is the classic way that we get from a classical bit, initializing a bit just to a value of 0, a qubit, and then putting it into a superposition of states, somewhere where it might collapse to either value. And square root of knot is very similar to that gate. It's called that because when you square it, it looks a lot like the knot gate. All right, so I talked about unitary transformations. So why is it important that the transformations that we look at are unitary? Well, that's because in quantum physics, we have to have transformations that are reversible. So given an output, we need to be able to go to input. If you look at the AND gate, classical AND gate, there's no way to do that, right? If you have a 0, you don't know what your input was. So that kind of gate is not allowed in a quantum circuit. So we can get around this though. So Toffoli gate is a reversible gate. We could have a quantum analog of this. Quick note on this notation, this is called Ket notation. I don't think it's too important for us to get into Bra-Ket notation, but this basically just represents the state. So the state of bit x. This diagram indicates that this is a controlled bit. So the value of this and the value of this bit control what happens here, and this is a controlled knot. So if both of these are 1s, this bit will be flipped. Otherwise, it will not be flipped. So how can we, this is the matrix version of that. Just to give you a feel for it, this is actually a relatively simple one though, because it looks a lot like an identity matrix right up until the end, right? Because nothing happens unless both of the first 2 bits are 1, in which case that last bit gets flipped. So it's just the intuition for that transformation. So we can actually construct a reversible AND gate using this. If we just initialize this last bit to 0 always, then the result will, then this NOT gate will only flip if both of these are 1s. So this is actually equivalent then to bitwise AND on these 2 guys. And it's reversible essentially because we're just bringing the inputs along with us. So we know what the inputs are because they just come along for the ride. So, how are we going to construct a quantum algorithm? Well, so typically what we'll do is we'll start in some classical state, some state that we know, just zeros and ones, classical zeros and ones. We're going to put that system into a superposition of states. So we're probably going to run it through some Hadamard matrices, some rotations. Then we will act upon the qubits using unitary operations. So in some cases, we might have to take like a classical operation like and translate it into something reversible that we can do in a quantum circuit. And then we're going to measure some or all of the qubits, and they will collapse to some value. And based upon the value that they collapse to, we will infer some information. And then at this point, we may repeat the process. So this is, in some algorithms, you'll go between quantum and classical. All right, so we'll start with